What if I told you there's a machine that can travel from New York to Washington, D.C. in under an hour? That's roughly the time it takes most of you to commute to work. What if I told you this machine runs on electricity? No fuel, no explosions, just silent, smooth speed that pins you to your seat, like a roller coaster designed by very polite engineers. And what if I told you this technology has been around for 60 years, yet most people have absolutely no idea how it works? Welcome to the world of high-speed rail. Today we're going inside the engineering marvel that connects cities at impossible speeds. We'll explore the wild history of how it all started, the rivalries, the disasters, and the sheer stubborn genius that brought us from steam to 300 miles per hour. We'll break down exactly how these trains work. No engineering degree required. I'll explain it so clearly, you'll be able to explain it to your confused uncle at Thanksgiving dinner. And we'll look at where this technology is heading, because the future of transportation might be faster than you think. This is What Is, and you're watching the answer. History and origins. To understand high-speed rail, we need to understand something fundamental about human nature. We've always been obsessed with going fast. The story starts, as many stories do, with competition. In the early 1960s, Japan was rebuilding. World War II had devastated the nation, and the economic miracle was just beginning. But there was a problem. The Shinkansen, the bullet train, was supposed to be impossible. You see, in the 1950s, train technology had basically plateaued. Trains in Europe and America topped out around 100 miles per hour. Engineers said that was it. That was the limit. Rails couldn't handle more, they claimed. Physics said no. Japan said, hold my sake. In 1957, a group of engineers at Japanese National Railways did something radical. They looked at the problem backwards. Instead of asking, how do we make trains go faster on existing tracks? They asked, what if we built entirely new tracks specifically designed for speed? It was an absurd idea. The cost would be astronomical. The engineering challenges were seemingly endless. But here's where the story gets good. They didn't just succeed. They revolutionized transportation. The 1st of October, 1964, just in time for the Tokyo Olympics, the Tokaido Shinkansen opened. The train was called the Zero Series, and it could travel at 130 miles per hour. That might not sound impressive today, but in 1964, it was absolutely unheard of. The old railway between Tokyo and Osaka took 6 hours and 40 minutes. The Shinkansen did it in 4 hours, for a journey that, by car, would take you 7. Now here's the part that blows people's minds. That original Shinkansen line has never had a single passenger fatality. Not one, in over 60 years of operation. Let me say that again. 60 years. 0 deaths from accidents. Compare that to driving, where approximately 38,000 people die annually in the United States alone. The Shinkansen is quite literally the safest form of transportation ever invented by humans. But Japan wasn't alone for long. France entered the race in 1981 with the TGV, the Train à Grande Vitesse, and they made it look easy. The TGV hit 236 miles per hour during testing, setting a world record that would stand for decades. The French didn't just copy Japan, they improved the concept in a way that nobody expected. The TGV used something called active tilt. You see, when trains go fast around curves, they experience centrifugal force, the same force that pushes you to the outside of a car on a sharp turn. Traditionally, this meant trains had to slow down for curves, or passengers would get thrown around. The French said, what if the train leaned into the curve? And they built it. The TGV could tilt up to 8 degrees, allowing it to maintain speed through curves that would force other trains to crawl. The competition heated up. Spain built the AVE. Germany built the ICE, the Intercity Express. Italy built the ETR. Every major industrial nation wanted a piece of the high-speed revolution. But here's the question everyone was asking. What about America? America tried. In 2000, Amtrak introduced the Acela Express, their attempt at high-speed rail. And it was fine. It was fine in the way that your friend's attempt at home cooking is fine. The Acela tops out at 150 miles per hour. In certain areas, when conditions are perfect and everyone behaves, and the moon is in the correct phase. The problem is simple. America didn't build new tracks. They tried to retrofit old ones, and you can't make a thoroughbred racehorse out of a farm pony, no matter how much makeup you put on it. But don't lose hope. We'll get to the future. I promise. Alright, before we dive into the engineering, because that's what you came for, right? Let's take a quick pit stop. If you're finding this journey through the world of high-speed trains fascinating, hit that like button. It helps more people find this video. And honestly, it makes my day. And if you want to explore more What Is content, subscribe and hit that notification bell. We break down the most incredible technologies and ideas, and I think you'll like what you see. Now let's get into the good stuff. How it works. Okay, let's get technical. And I promise, I will make this make sense. The first thing you need to understand is something called steel on steel. That's exactly what it sounds like. A metal wheel on a metal rail. There's no rubber, no tires, no cushioning. It's just two pieces of hard metal pressed together. Now you might think that sounds inefficient. You'd be wrong, and here's why. When you drive a car, you're fighting something called rolling resistance. The tire squishes slightly as it rolls, absorbing energy like a sponge. That's why cars use so much fuel. A huge chunk of the engine's power goes into just squishing the tires over and over. With steel on steel, no squishing. The wheel is hard, the rail is hard, and they roll with almost no resistance. It's literally the most efficient way to move humans over land that we've ever invented. But here's the catch. Steel on steel has terrible traction. That's why your car wheels spin when it's raining. The rubber slips on wet asphalt. Trains solve this with weight. Trains are heavy, immensely heavy. A single locomotive can weigh over 200 tons. That weight presses the wheels into the rail with enormous force, creating enough friction to move the entire train. Now let's talk about how high-speed trains actually propel themselves forward. Electric trains like the Shinkansen and TGV get their power from overhead wires, those weird cables you see running above the tracks. The train has a device called a pantograph, essentially a metal arm that reaches up and touches the wire, completing an electrical circuit. This is where it gets beautiful. The train's motors are what are called three-phase AC induction motors. I know, that sounds like something you'd find in a Transformer movie. But stay with me. Here's the simple version. When you run electricity through a carefully designed coil of wire, it creates a rotating magnetic field. This field pushes on the train's wheels, causing them to spin. The key insight is this. Unlike a car engine, which has a limited number of power strokes per second, an electric motor can generate maximum torque, the rotational force, at any speed. That's why electric trains accelerate so quickly. In a petrol-powered car, you have to rev the engine to generate power. There's always a lag between stepping on the gas and feeling the acceleration. In a high-speed train, you step on the power and you feel it instantly. The motor goes from 0 to maximum torque in milliseconds. Now here's the part that really matters for speed. Aerodynamics. At 200 miles per hour, air resistance is the biggest enemy. Not friction, not the rails, the air itself. A train going 200 miles per hour is pushing thousands of pounds of air out of the way every single second. Engineers spend years perfecting the shape of high-speed trains to cut through the air like a knife through butter. Look at the nose of a Shinkansen. That long pointed front isn't just for looks, that's calculated aerodynamics. The train is literally designed to split the air in front and guide it smoothly around the sides, minimizing turbulence and drag. But aerodynamics creates another challenge: stability. At high speeds, airflow can actually lift the train slightly off the tracks, kind of like an airplane wing. That's dangerous. If the train lifts too much, it could derail. Engineers solved this with careful design of the front wheel arches and subtle spoilers that direct airflow downward, pressing the train firmly onto the tracks. Some trains even have small wings, Yes, really, that extends slightly to generate downforce at speed. Now here's the system that makes high-speed rail possible. Signaling. At 200 miles per hour, a train can cover the length of a football field in just 2 seconds. There's no time for a human to see a problem and react. Everything must be automated. High-speed lines use something called automatic train protection, a TP. The system constantly monitors every train's position, speed, and the conditions of the track ahead. If anything is wrong, another train too close, a track problem, anything, the system can automatically slow or stop the train. This is why the Shinkansen has never had a collision. The computers are faster and more precise than any human could ever be. One more thing, because this is the question everyone asks: how do they stop? High-speed trains have multiple redundant braking systems. There are electric brakes, which use the motors in reverse, acting like generators to convert the train's motion back into electricity, sending it back into the power grid. These are called regenerative brakes, and they're incredibly efficient. There are also disc brakes, exactly like in a car, but much larger and more powerful. And on some trains, there's even an emergency magnetic brake that pulls the train against the rails using magnets. The result? A high-speed train can stop from 200 miles per hour in roughly 2 kilometers. That's about the length of 20 football fields. Fast? Yes, but safe above all. And that brings us to the final question, the one that matters most. The future. Where is high-speed rail going? The answer might surprise you. The next frontier isn't just faster trains, it's something called maglev, magnetic levitation. A maglev train doesn't touch the tracks at all, it floats. Here's how it works. The track contains electromagnetic coils, essentially powerful electromagnets. The train has its own magnets. When the train approaches, the track's magnets activate, creating an opposing magnetic field that lifts the train slightly off the surface. No contact, no friction, no noise. The Shanghai maglev currently operates at 268 miles per hour, the fastest commercial train in the world. Japan's L0 series maglev has tested at 375 miles per hour. 375 miles per hour. That's faster than some small aircraft. But even that's not the wildest idea. There's something called Hyperloop, a theoretical system that would move pods through near vacuum tubes at speeds approaching 700 miles per hour. The lack of air means almost no resistance. Theoretically, a pod could travel at speeds faster than sound. Now, is Hyperloop real? That's complicated. The engineering challenges are enormous. Maintaining a vacuum tube hundreds of miles long, dealing with expansion from heat, safety concerns, and of course the small matter of cost. But companies are working on it. Tests are happening. And in the world of engineering, never say never. Back here on Earth, the immediate future is already exciting. In France, the next generation of TGVs, called Avelia Horizon, will enter service in the mid-2020s. They use distributed power, motors throughout the entire train instead of just in the locomotive. This reduces weight, improves efficiency, and allows for more capacity. In Japan, the Shinkansen maglev line is under construction, connecting Tokyo to Nagoya. When complete, the journey will take 40 minutes, down from the current 90. And in America? America is trying. The California high-speed rail project has been controversial, delayed, and expensive. But here's what's important to understand. They're building it. The first section between Bakersfield and Merced is under construction. It will eventually connect San Francisco to Los Angeles in under 3 hours. And other projects are following. Texas is studying high-speed rail between Dallas and Houston. Florida has Brightline, Nevada has plans. The point is, the interest is there, the demand is there. It just takes time and money to build. But here's what I want you to take away from this. High-speed rail isn't just a technology, it's a philosophy. It's the belief that we can connect people across distances, not as fast as planes, but fast enough to make car trips obsolete. It's the belief that transportation can be clean, efficient, and safe. In a world increasingly worried about climate change, high-speed rail is one of the most environmentally friendly ways to move millions of people. An airplane produces roughly 10 times the carbon emissions per passenger mile as a high-speed train. A car? Even worse. When you ride a Shinkansen, you're not just traveling. You're participating in one of humanity's greatest engineering achievements. You're moving at speeds that 60 years ago, scientists said were impossible. And you're doing it safely, comfortably, and efficiently. That's the future of transportation. And it's already here. So now you know. You know the history. How Japan said, "Hold my sake," and built the impossible. You know the engineering. Steel on steel, electric motors, aerodynamics, and automation working together in perfect harmony. And you know the future. Maglev, Hyperloop, and a world more connected than ever before. If this story of human ingenuity fascinates you, there's more where this came from. What Is exists to break down the most incredible technologies, ideas, and concepts, explained simply, told engagingly, and always with a bit of fun. If you learned something today, hit that like button. It helps this video reach more curious minds, and that makes this all worth it. And if you want to join the journey, subscribe to What Is, and hit that notification bell. Every day, we're exploring another question worth asking. Until then, I'll see you on the next one.